Hello, Michelle Q. Hello, Katie M. Hello, Emily H. I'm going with a good afternoon. Okay, all right, awesome. Hello, Maria Z. See, I went straight to, okay. Good afternoon, Gina. There's Cheska. And good afternoon. Oh my God, she does, okay. Yeah, good afternoon, Mohammed. Oh, and good afternoon, Alan, Paulina. Um, Good afternoon, Brooke. Good afternoon, Freddie. Now I know what he looks like. Good afternoon, Mitch. I know a lot of you look like, which is good. Okay, sorry, people are here. I'll stop. No, I won't. Good afternoon, Michelle Q. I know what her uh yeah, looks like. Okay. Good afternoon, Marilyn. Good afternoon, Alan. I said that. Okay, I'm in the chat. Good afternoon, Victoria. Afternoon, Maria. Someday we're going to get an adjective out of that person, I'll tell you. Good afternoon, Katie. Good afternoon. Oh, she smiled. I say, I'll take a smile instead of an adjective. All right. Good afternoon, Paulina. I said because video and chat. Good afternoon, Michelle F. We definitely get adjectives out of her. We want. Did I say Alan? Wait. Why is Jessica? Wait, what's wrong with Alan? Did I not say Alan? I'm sorry. Well, good afternoon, Alan. Okay, and good afternoon, Stephanie. I didn't say. Okay, I'm going back and forth between the chat. I don't know what happened. Okay, wait. I don't. Okay, well they'll explain it to me. So good afternoon. I'm going to stop. No, I won't. Good afternoon, Allison. Oh, it's rare. Is it rare to? Okay. Well, I feel like. All right. Well, you. Okay. You're just being annoying. Okay. Okay. Oh, yeah, I don't think it's a no, Alan. I feel like you're in this class for what it's worth, if that's a metric. No, I feel like I see. Yeah, I do. Maybe, yeah. No, I've seen his camera. All right, well, whatever. I mean, I'm not going to get, okay. But the important thing is something. Okay. Um, no, Alan, I know who you are. Okay, anyway, all right. And boy, we know who Cheska is, don't we? I mean, what? Okay, no, wait. Okay, there you go. Right. Okay, thank you, Katie. See, Katie, that's a collegial. No, which part? What I said? Well, I'm just saying you're very present, like me. I mean, you're a character. I mean, did I say that? I'm gonna stop. When I'm in a hole, I'm looking, I should not look at her face. No, it's a compliment. Anyway, I'm gonna stop. All right, here's the deal. Wait, did I say hello to everybody? Honestly, I think I did. I did. And if I didn't, you'll let me know. Hello, everybody. All right, here is the deal. First of all, you'll notice that a lot more things have populated the Google Classroom, like Professor Tally has like put in a bunch of all her lecture materials, which is very nice. And that's all just for help because, her section has an exam coming up also. So we're just trying to give you as much resources as possible. None of it, you get it, right? I mean, it's just whatever. So you could see things from a different perspective. And anything you missed, blah, blah, blah. So as far as I know, we did establish, I'm going to post the actual exam this Thursday before 8 p.m., right? Then we agreed you'll have not till next Monday, but till next Wednesday class time to get it back to me. I think we established that. I think that's what's written in Google Classroom. But this was a change as of last class. So if you weren't here last class, like please check the Google Classroom or, there was a change. Well, I guess you would know that by now. Anyway, the exam will be no longer than what's in the practice exam. It will hopefully be shorter, but it definitely won't be longer, and it definitely won't include anything really that's not in the practice or yeah. Again, most of you had me before, so most of you know this. The one thing I just want to reinforce. Well, the one thing I want to reinforce is that with an exam, hold on, are we recording everything? Yeah, okay. With an exam, you do have to be on time. Like I know I'm super loose on purpose about like most other deadlines, and homeworks, it's still true that you can still be revising and uploading old homeworks. You still can for more points, or maybe many of your cases, IOU points still. None of that changes, even when none of that changes. Like, as you see, the exam is very much based on those homeworks. So certainly using the homeworks to like study and prepare and get them right is helpful. But don't even worry. This is not the time to be scrambling to like hand in old homeworks. I don't think. I mean, unless it gets your head organized. Just worry about the practice exam. What I'm trying to say is that I'll still take old homeworks later and all of that. That remains kind of a loose aspect of this class, but the exam itself has to come in before we start class next Wednesday. I'm just reminding this to anybody who like hasn't had me before or whatever, because it can be very, I know it can be very confusing, you know, how loose I am about some things. So I just want to be clear that the exam does have to come in by 12:15 p.m. a week from this Wednesday. Correct me if I'm saying anything wrong. That means, and then two things. You turn it in before 12:15 on Wednesday, and then you show up to class like as though that class period were our exam period. Like you are responsible to show up and be in class the same way you always are. I mean, like that doesn't mean you have to show video, but you have to be here for the class as though that were our exam period. And again, just to reinforce anybody who's new, so you can't submit the exam and run. And the main reason for that is so that your colleagues see that you're here just like they are, and that you're not still working on the exam, if you follow what I mean. And if you don't, text me or email me, but like it's part of group solidarity that you all show up and sit through the period so that you all know that none of you got some unfair advantage or something like that. Oh, good morning. Thank you, Yavi. Good morning. Good to see you. Okay, so on the one hand, it is strict. It's stricter than I am about other things. You have to turn in the exam by 12:15 when it's due, and then you have to show up and sit for classic. Obviously, if you come, you know what I mean, the way you always do for Zoom, like have your box on so your colleagues know you're here and that you did the exam. And you might have done a lot of it with them. Fine. And I'll remind everybody about that in a second also, or today and Wednesday. Like basically this week, we're going to try to help make sure you're as prepared for this exam in every way as possible. I'm not really going to do much more other new material, even though I probably should. So forgive me, but I just want this to be clear. What the heck was I just saying? So the flip side also, again, I know I've said this before, but again, not everybody, some people here are new. You can do anything you want to do this exam. It is understood that you can go on the web, that you don't have to time yourself, that you don't have to sit in weird conditions. You can go on the web. You can look at your notes. You should look at your notes. You can look at my old YouTube videos or the class videos, even like while you're sitting writing it down. Like, and you can even talk to your colleagues. To some of you, that is still crazy, probably, but that's why I want to be super clear about it. You can do whatever so think of this more as like a research report or something. You know, it's think of it as a paper or a presentation. You can get, really, I guess that is what it is. It's a written presentation. You can get any kind of help you want. And the more that you guys work together, honestly, the more happy I am that you're teaching each other and working through physics. You can do that. But the bottom line is, therefore, and I'll say this probably more times, the bottom line is, realize that I know that you did that we both know that that's the arrangement. It's an open source arrangement. Therefore, the standard for excellence is not correct answers, right? The standard for excellence is, are you showing me in your work that you really understand this work? It's a presentation. Think of it as I could bring you into my office and grill you vocally on everything you wrote down. Like at the end of the day, it doesn't matter where you get your information, just like a prison presentation or a conference presentation. It doesn't matter where you got, but it matters that you really, really are in command of that information by the time that you write it down. So your goal in the exam is to convince me to be in as detailed as possible and showing all your work and being as clear as possible that you get what you're talking about, like the process. I already know that you know the answer, right? So so by the time you help, whatever, I'll stop in a second. You help each other, please, sure. And talk to other people who've already talked to class, taken the class, sure. Find all old videos you can, sure. But then you sit down in your handwriting and in your different colors as possible and in your way of making pictures and in your approach to the English language, you sit down and you present your mind to me. You're like, Yaverbaum, this is how well I know and can explain all this stuff. Like I could teach this to my 3rd grade sister or like whatever, right? Or my dog. Like that's how well I understand it. And last point on that too, and believe me, I'm saying everything that I learned the hard way in graduate school all the time is that, which is you make it as thorough as you can, show your understanding as thoroughly as you can, but you make it as easy and clear and inviting for me to read as possible. So the two standards are, again, it's like a presentation. The 2 standards are you covering all the bases and showing that you really understand every step? That's standard number 1. But standard number 2, are you giving me a document that I could sit down with, or Mercedes could sit down, or Hema, or like anybody who knows physics, but doesn't necessarily remember the exam questions, could just sit down with and absolutely follow what you're doing from beginning to end of each problem, like you in one self-contained document. Again, as though you were sending it to a journal. Or to a, right, or to present, like you're saying, like here, given a mass on this spring, blah, blah, blah. The question is, could we figure out the velocity? Well, here's how we do it, blah, blah. So I should be able to mark up your whole, really, the standard is, can I grade your whole exam and be blown away by your understanding of this stuff without me having to look at anything else, like at the exam? Can I grade your exam? Can I be sucked in and want to read your exam and be brought into your mental world without me having to look at anything else in order to do it? The more easily and happily I can do that, can come into your exam and see how well you understand, then the more happy you are at the end. Okay, that's my big speech. I hope that's what you're trying to do. It's proving is that it's like presentation. Okay, wait, I'm looking at the chat. But now, having said that, we're going to talk about it your way. Which just because we had like friction right there. Okay, I don't get it, but okay, I may swear to do. Okay, all right. So let me start with this. So having said, well, first of all, all right, is that for? I mean, again, I know most of you have had me before, and I think you wouldn't really be. I think most of you figured out how to make it work. But just raise your electronic hand if you get my basic message about how the exam works. Yeah. Uh-oh. Okay. All right. Thank you. See, Al, okay. Thank you. Who said Alan's not in this class? Okay. Thank you. Yes. Okay. Good. That works for me. Thank you all. I won't even mention you all by name, except that I will. All right. Therefore, I'm going to say now, since you have a practice exam, there's a video that walked through. I don't know if my video, you might want to tell me in the chat. I don't know if the video walked through exactly the same exact questions as that practice, but I think they were close, and that's what your real thing would be, close, not exact anyway. So hopefully that video is helpful. So I'm going to start by saying, oh, wait. I'm looking in the chat. Wait, this is good. Is it? It did. It was good. Great, great, great. Great. So then why do people in the other class can? Okay, great. That's what I originally thought. And then someone was, all right, thank you, Maria. Thank you, Katie. That's points right there. All right. That also is a clever way for them to indicate that they've actually seen it. So that's good. So I'm going to start with right now, just even though I know we also have class Wednesday and the thing will be posted Thursday, but I'm going to start right now. Are there any, I'm going to say this, any question at all that you have about the exam, particularly assuming that you've even looked at the practice exam, that you've been trying it, any question that you have about the practice exam or the video or whatever, big or small, I want you to put in the direct chat right now. Well, oh, you are. Okay, good. I'm going to give you a couple of minutes to put in the direct chat. And I'm saying direct chat because I'll just, well, for 1,000 reasons, but I may not answer all of them now. I'm going to sort of triage, or I'm going to decide like which ones I can answer the most quick, efficiently first. But any okay, I'll at least read them all. So I'm going to pause. Take your time. Any question that you have about the practice exam or the practice exam video or the procedures or anything, put the questions in the direct chat right now. I'm going to wait like a long time. And I will tell you that the more specific your question is, the more specific it is, the more chance I could actually answer it like in a helpful way, right? If it's just like, could you walk through the thing? I can't do that efficiently. I mean, I tried already on the, so I'm gonna wait. Any questions that I'm gonna put in the chat, in fact, because there's one. Okay, I'm gonna wait. I did see one question already in the direct chat. So if there's one person, so that person, I do see your question. And if it ends up being the only one, I'm gonna do it. I see two questions in the direct chat. They're both good. I'm gonna still wait though. This is your chance, and I'm not promising we're doing this for both Monday and like, if there aren't a ton of questions today, I'm not. This may be the opportunity. So take a minute, all of you. I'm pulling it up meanwhile. All right. Okay. This. If more questions occur to you, I would definitely put them in today. Again, kind of assume that you won't necessarily have a chance to ask these questions on Wednesday. You might, but today would be the day to ask these questions. So I see two so far. One of them I can answer more quickly than the other. All right, I'm going to read this out loud. It's a very fair question, and it's a very sort of common question. Like, people are often concerned about this, so it's a good. So this is the question: if we're answering something like question 1 on the midterm, Q1 number 1. In fact, wait, let me in fact look at that right now. I think I do know what the person's saying, but oh yeah, right. So they're saying like if you go to number 1. All right, I'm even going to screen share to make this as clear as possible. I think this is it. Yeah. So like, here's question 1 in the exam, right? And of course, there's no guarantee that the exam's in the same order as this. And oh, sidebar, you can hand things in and, well, you can do things in any order you want. Obviously, this is a take-home, open-ended thing. But two things about that. I mean, of course, you can approach things in any order you want, but number 1, since it is take-home and untimed, then I would ask you, please, once you put it all together, put it in together in order. Like, again, part of your job is to make this as easy and inviting on me to look at the document as possible. It's going to be a long document in many of your cases. I mean, even if the test is shorter than this. So put it in order, number one. Number two, definitely the thing that's going to separate people who do well on this from people who do better versus people who do less better. One thing that's going to separate is who gave themselves time to do a rough draft and a final draft. Like, honestly, and I've been both people in my life. Believe me, I know both scenarios. And some of you probably don't know both scenarios. Some of you probably are always doing things, whatever. Here's the thing. It makes a huge difference, an enormous difference, to give yourself enough time to do a draft first. That's you thinking things through and you looking at stuff and talking to your friends and blah. And then actually giving yourself time to sit down and then make a final copy once you have all the content right and you know what you're trying to say, then making one that really is good and looks good and is easy to navigate. That makes a huge difference. Now, why am I saying all of that? But it's advice and it's like pro tips. And again, remember here, this is like, it's all, there's a little bit of discretion that's left to me in grading a thing like this, right? You get my, it's not just black and white. So I would encourage you to take steps like that. Now, why I'm saying all that is because there's this question here in the chat about question one, number one. And it's a really good question. So that you're looking at, I mean, so you see what he or she means or they mean by question one, part one. And now here's their question. If we're answering something like question one on the midterm, how far back in what we've learned so far do we have to go in order to explain the equation x equals x naught cosine omega t? Do we have to go all the way back to the findings from homework 1A and the beginnings of 1B where we find work and the path integral of force, etc.? Or can we start by just explaining the derivative, the differential equation, d2x dt squared equals negative k over mx, by saying something along the lines of recalling the information that we learned from a mass spring system? Okay, this is a brilliant question. I mean, it's a great question. It's a super important question. It's the kind of question that's being asked by someone who does presumably go to presentations and conferences, because they know from asking this, it's clear that like kind of the issue once you do know something is like, yeah, how far back in what you're explaining do you have to go? What can we assume is given knowledge and what we can't? Now, that is a very good question on an exam like this. And here's the reality. Specifically because we're talking about question one, part one, at the beginning of your exam, the big answer is the more you can go back and explain, absolutely the better. Yes. Like you don't just want, at the beginning of the exam, it's true, you don't just want to say, recalling information learned from a mass spring system, Let me be more specific. I might even write this down on the board in a second, maybe. Like on this question that we're looking at right here, what I'm expecting you to do is, yes, go back and re-show what you did at the end of question 9 of homework 1B. I would like, in part of the point of this exam is somewhere in this exam, you are absolutely going to show where we got this differential equation from. Like you're going to do that thing of, I'll say it now, I'll try to write it down in a minute, but if I can't, yes, you would do something like, well, F equals negative kx. For a mass spring system, you'd write F equals negative kx, F net equals ma, therefore negative kx equals ma, therefore negative kx equals m, and I'm sorry, a triple, if I'm going too fast, tell me, that's fair. Also, obviously you can re-scroll this video, but I'm literally telling you, yes, somewhere I want to see, I assume, I'll say it again in a minute, but what I assume is like given or fundamental in this course, what's given is F net equals ma and F equals negative kx. Like, yes, that is like knowledge we have going in. A lot of that stuff we did about energy and path integrals and all that, yeah, a lot of that is important when we get to energy questions. But you, like, if you were to say anything about kinetic energy or potential energy, you would have to walk through those path integrals. You would. But that's for answering questions about energy, which right now at this moment, you're not. So for this context, what you have to start from is F equals negative kx, F net equals ma, a, like a triple equal sign, d2 dx dt squared, like the definition of A is second derivative of position with respect to time. So those three you set up and like say a word or two about each one, like this means this means that. These are GDPs, right? Then you put it together. So now you have you put it together and you do algebra. So d2x dt squared equals negative sign, parentheses, k over mx. Then, yes, like we did in homework 1B, question 9, you don't have to do like 85 pages, but you say a couple things like, this is a differential equation. This means we are looking for a function of x such that its second derivative equals negative times a constant times itself. Like somehow in your words, say we're looking for an x that obeys or satisfies or solves this differential equation that I just got from f net equals ma and f equals negative kx. And then you say something, you do like we did, you make a little, like say, let's try cosine. Like maybe give a reason. Let's try cosine, make a little sketch of a cosine graph with the axes labeled. And then try, and again, you have notes from this and everything, but yes, one time on this exam, right around here at the beginning, yes, you're going to then like try cosine and like we did in homework 2, you're going to take two derivatives of you're going to write out the cosine. You might, if you're really looking for pro tips or you're really with me right now, you'll do exactly what we did in the class, which is you'll like write out cosine, but then you'll notice, oh, unit wise, we need a constant here and we need a constant there because you can't take the cosine of a second. So it's got to be cosine of something times t, right? And blah, blah, blah. And again, anything I'm saying now, if it's meaning anything to any of you, if you like know what I'm talking about, but you're a little fuzzy, you can, this is your time today. This is Q&A day. So you can still stop me or put something in the chat. But yes, the outline you're looking for is you try cosine, you talk about the units, therefore you make constants. So you're having something like x equals x naught cosine omega t. And then you take two derivatives of it with respect to time to show that it works. And that when it works, when after you take two derivatives of cosine, that it works, that it satisfies Hooke's law, the differential equation, then you conclude, aha, this works as long as, or if and only if, the omega in the cosine function is the square root of whatever that constant was in the differential equation. Like you say that, right? And this is a lot. I know it's a lot. That's why this is an exam. Like, so you do all that. Now you have, fine, now we see, whenever we have this differential equation, now you can like circle back and say, fine, if we have a differential equation of the form d2c dt squared equals negative constant times c, then we can conclude that c is equal to c naught cosine omega t, where omega is the square root of that number right there, that 98596 number, right? Hopefully everything I'm saying right now is similar to what I said on the video. And then you get the answer. Now I'm just about done. So to back up, what I'm saying on the one hand is, for the person who's asking this question, great question. Yes, especially on question 1, part 1 of this exam, like especially when I open up your exam and nothing has happened yet, I totally want to see you go to town on what that whole differential equation relationship and why it works, where it comes from, how it works at the beginning of the exam. You don't have to do the whole potential energy thing and all the integrals and all that, because that's like goes to a different type of question. But this, yes, please. And anybody who's listening to me, like if you're going, so yes, at the beginning of the exam, yes, yes, and yes. Then once you've like hammered down once like that at the beginning of the exam, then throughout the rest of the exam, wherever you're using that knowledge, then you can always say, see page 1. Or whatever, like literally, like refer to your own document. Say like, well, now that I've established that, like we're good. Okay, so again, in the manner of a presentation or a conference paper or something, like you got to show me, you got to take me. You have to assume I know physics, but I don't know the physics that you're doing, like, or I don't know what you're trying to do. So you do it. Then from then on, you don't have to do it a million times. So this also all goes to say, I mean, again, and this is not a like. This is exactly the kind of question I feel like it's useful to you to hear. I, the long and short of it is, that's also why you really want to make a final draft and you want to do this exam in order. Because if you give me big chunks of derivation like that right at the beginning, if you establish like the whole motor of simple harmonic oscillation and differential equation, like in the early stages of the exam, then you're off and running for the rest of the exam. It gets easier and easier for you to do stuff and for you to communicate stuff. And it gets easier and easier for me to read. And also, quite frankly, again, like conferences, then you've also sort of bought me to your side right from the beginning. Like once you bring me over to your side at the beginning, then of course also I'm going to be more chill as I'm reading it from then on. Like it, you know, the motor has been built. So if that sounds a little much, it is a little much. If that's the point of an exam like this, that's what will separate the wheat from the chaff, but front load it. Okay, hopefully that's sort of answered now. Okay, great. Okay, I'm seeing in the direct chat. Okay, great. Now any of the details of what I just said, I might be happy. I think they're all in the videos and everything, but take that as a road. That was literally the roadmap too. So for any of you who watches this again while you're studying, like, yeah, those are the bullet points that I'm looking for. So that's what you want to make sure you really understand. I mean, throughout, like that's the theme of all this. Now that was one. Okay, so thank you for asking that, and thank you for acknowledging my answer. So that was one question in the chat. There's another one that came early. Well, I'm going to tell you. I guess I'll tell you the questions. Another question in the chat is, it says in the chat, question 3. Now I'm intentionally saving that. It's fair to ask that. Like so he or she or they is asking for me to talk about question 3, and I totally understand why, because that's really, in some ways, the hard, like that takes all this concepts that we've done in lecture, but it applies it to a thing from the lab. I mean, a phenomenon from the lab. Also, I'll admit that question 3 is also perhaps not the question 3 is, yeah, maybe the most challenging in a way, because also I mean, it's not by accident, but it requires some some memory of some physics 203 concepts that we can't get away with not invoking in quite, like you have to remember your free body diagrams and stuff like that, because they never do go away in physics. So I definitely understand why 3 is the most intricate, but it's like long problem, right? So I'm seeing if I can do other shorter things first. I may or may not get to do a full walkthrough of it today. But I'll try to do some highlights of it if I can. But also, I think, and you can tell me in the chat, I think I do walk through. I think that's actually main point of the video, is that I walk through question 3 in the video. So at least let me know in the chat if it is there in the video. Then maybe you could give me more of a specificity, like what exactly in question 3 do you want me to spend time on here? If you can do that, that would help. But I'll still try. Let me just see but there's other questions now. So let me just see. Oh, this is interesting. Oh, this is in the public chat. Okay. What does the negative sign mean? Oh, for such problems? Like I remember in physics 1. Okay, so negative definitely means direction. Yeah, so I'm reading this Muhammad's question, and thank you for the question. I'm reading, but again, you're all welcome to use a direct chat, especially before exams. I know people maybe are more comfortable in direct chat, but negative definitely does mean direction. Yes, in the specific case of, like in this problem that's on the screen right now, well, I don't know if this is exactly what you're asking. Like, wait, maybe. All right, I think I can answer this somewhat help. I'm going to switch the screens. I'm going to do a quick sketch of the thing that I just rushed through and said, like what I'm expecting you to do, at least at the beginning of the exam. Oh, and by the way, the other reason I'm excited about that question that I just answered is the converse of everything I said is, it's not just that that's a pro tip. I mean, yes, it's a pro tip, but it's also that if you don't do any of that, if you literally just put answers on this thing or don't put the 5-step method and stuff, like you have to, again, I think everybody understands this, but I've gotten into trouble with this a couple of times with students, a couple of times in the past. If you just put answers throughout this exam, or you put a bunch of solutions like from websites, like Chegg or whatever, like if it doesn't look like that's not sufficient. It doesn't matter if the answers are right. And it's not about cheating. Like I don't have to, I'm not going to get in, we're not talking about ethics as such. I'm just saying that this exam is about derivations, proofs. So you got to do the proofs to do the exam, if that makes any sense. You can't expect to get 100 just because you have correct answers. I mean, I guess that's all I'm saying. But now, to Mohammed's question, how do I do this? Wait, to Mohammed's question, I want to switch the screen. I want to write out something for him, for everybody. Oh, like here. Oh, he even wrote. Okay, okay. Yes, good, good. I'm just trying to switch the screen. Okay, like here he wrote. Oh, it's kind of rough. Oh, okay, I'm also seeing the chat. Okay, I hear you about the pendulum thing. Okay, so what Muhammad's asking, like all right. All right, so Muhammad's asking, what's the deal with that negative sign right there? I'm gonna try to answer this in some like, okay, I take it that means like, what does it mean, and what am I supposed to do with it? Well, what you're supposed to do with it is, first of all, notice that it's there. The first thing that it's doing by being there is it's telling you that this differential equation is the correct form for simple harmonic oscillation. Like first thing, and again, I'm trying to write this in a style that you would try to write to me in the exam. First, when I switch to Z's now, to everybody, remember, whenever I switch to Z's, I'm making a general point about anything that could be the measurable dependent variable Z, right? So I'm switching to the general form, and I'm saying that anything of that form where omega squared is a constant. So anything where the second time derivative of a variable equals a negative sign times a constant times that variable, anything of that form is simple harmonic oscillation. To be very specific, if it were this form, if it looked like this, if it didn't have the negative sign, then it would not be a simple harmonic oscillator physically, and all the math that we have done about with cosines and all that would not apply. Okay, so first of all, just on a test-taking standpoint, I mean, just in terms of taking this exam, what the negative sign there is telling you is, it's telling you that this value of C does go back and forth and back and forth and back and forth like a mass on a spring. It means that you can do all the math that we're sort of talking about right now and make all the predictions with period and frequency and all that. If the negative sign weren't there, it would still be math. It would still be a differential equation. It would still mean something. In fact, it would still mean something in physics, but it wouldn't mean this. Right? So the first thing is that the negative sign is telling you, okay, this is a simple harmonic oscillation situation. Even though I don't see a spring that's made of metal or whatever, even though I don't even quite know what C is, like, I'm like, you're reading this problem, it's about a capacitor and charge and like all this stuff that you might think, wait, did we ever learn about this? Like, I don't know anything about capacitors or charge, whatever. The whole point is it doesn't matter. Like, on purpose, doesn't matter. It's saying there's some system that you've never encountered before, you don't know anything about, but when you started making measurements on this value C, you found out that C did this thing. And this thing, as long as the negative is there, means that C is going back and forth in a cosine fashion, as though it were a mass on a spring. Okay, so number one, that's what the negative sign is doing. It's telling you that this is simple harmonic oscillation. But then number two, like why? And this goes now to the question that the other person asked at the beginning of this class, like where did that negative sign come from? What does it mean physically? What the negative sign really is coming from, it's really coming from this negative sign. It's really the negative sign of Hooke's law. It's the negative sign that means restoring force. It's the negative sign that actually means, like if you, I'm just doing this quickly. Right, if in the original homework 1 analysis of a mass on a spring, if the whole point of Hooke's law, it says that if the mass is to the right of the equilibrium, then the force will pull it to the left. Like this is where your Muhammad's original question comes in to play. Yes, negative means direction. Specifically, what it means is that the direction of the force is opposite to the direction of the displacement from equilibrium. That if the mass is to the right of the equilibrium, it will be pulled to the left. And if the mass is in the negative places, if it's on the left, then it will be pulled to the right. That's what that negative sign is. And therefore, the mass is going to go like that. It's going to oscillate, right? Quick thing. So mathematically, we said F equals negative KX, and we also believe that F net equals MA. So we said negative KX equals MA. Oh, and we also, I always forget to write this, but we also believe that the definition of acceleration is the second derivative of position with respect to time, right? So negative KX equals MA. So negative KX equals MD2 dx dt squared. Therefore, if I just now I'm doing this fast, but I want you to show me this at least once at the beginning of the exam, something like this in your way, once you understand it. So you get this, right? And so now notice d2x over dt squared equals negative constant times x. Like here, just write it next. Whatever that crazy number was. And there's a reason for the number. The whole point is that then whatever we believe that x is going to do, the value of x is going to go back and forth because of that negative sign, because that negative sign says x is always being brought into 0. Whatever x is going to do, we can believe c is going to do. So then you do this little thing, and I'm going to stop right here, but you say something like, we'll try x equals x naught cosine omega t. You explain why you're trying that. Then you take a derivative, you take another derivative, and you show that it all works. So you're ultimately trying to show, you're ultimately trying to show that whenever you have something of that form, then the solution is a cosine solution for which the angular frequency, omega, is the square root of that number. The whole thing only works if there's a negative before that number, that constant, because that negative means ultimately there's a restoring force like Hooke's law. So the whole thing acts like a spring. That was a long answer, but I'm just going to look. And I see there's other things in the chat. But did that, Mohammed, when you get a chance, let me know if that sort of answered your question. I've started becoming aware of the fact that sometimes if I answer too much, then it's even worse than answering too little. But okay, thank you, Mohammed. Okay, so great question. Now, 1:30. Still looking in the chat. Okay, so the person in the chat is talking about question 3. Says I was rushed to the end. That I'm not surprised. So I really don't know what is occurring. All right. Wait. Oh, okay. I gotta say, what Maria just put in the chat is super helpful to all of us, certainly including me. Okay, I will still try to address what private chat person is saying, but okay, I do want everybody, and that explains it because I thought I had done a detail, so I basically posted not the most ideal video. Okay, please, and I'll tell the other class this too, or please tell your friends in the other class. I think that's like really important that Maria's pointing out that the video on the midterm from summer 2023. Okay, I'll even try to, I'll even post that right now. Wait, that's really, because I knew somewhere I had done a full walkthrough of that summer 20. Okay, so 2 semesters. So that's more recent. Yeah, because even the thing that I posted was that. Well, okay, I'm going to post what Maria's saying right now because I do want everybody to get a detailed, and I know the pendulum thing is hard. And if I start going into the whole pendulum thing, I will never get to anything else. So, okay, it'll be worth it. 1 second. Oh, yes, it's after. So that video was later. I don't know why I didn't. Okay. Thank you, Maria. So give me a second to do this right now. I mean, obviously it's there in a place. I mean, she found it. I mean, it's findable, but yeah, thank you is to Maria, I definitely, yeah, thank you, Maria, for sure. And thank you, someone, Paulina, for thanking her. Okay, so summer, sometimes I look at this stuff and I'm like, it's sort of isn't it shocking how seemingly organized such a disorganized person can seem? No, I'm sure you're not shocked at all. And you're like,
To like kind of help your search for the video, I think Maria just posted it in chat.
oh, wait, someone just posted in chat. Oh, thank you. All right, great. Okay, this is great. And thank you, Katie, all right, so I will, no, this is it. See, this is why we're doing this today. I knew I didn't know what I didn't know. All right. Okay. Post it right. Again, obviously everybody can just take this link off the chat, but just so that it's like, because we also know that when you go down to sit to study, it's different. Okay. Now why this is really helpful is it means now I can actually try to say something specific about this problem right now, like without doing all this. So we're just about there. Okay. Okay. Thank you very much, all of you who just partook in that. All right, so now it's posted, so you should watch it. And now I'll say what's going on with that problem, especially at the end, or what the hook of the problem is. Okay. Okay. The hook of the problem. Let me just pull it now. Well, so I'm gonna here's what I am gonna like walk through it right now in a way, but I'm not gonna write anything down. That's how I'll keep it. And I will change screens. So you can see what I'm talking about. Okay. All right. So now we have a pendulum, right? So it's like lab 2. And the big upshot of this whole problem is it's trying to show the whole point, which is that harmonic oscillation is a type of system that's ultimately described by math, that anything that obeys the math of harmonic oscillation no, excuse me, anything that obeys the math of a mass on a spring then behaves like a mass on a spring, right? And to the point where the variable that we're measuring, the dependent variable, might not even be positioned on an x-axis. Like, so for a pendulum, right? So in other words, a pendulum, of course, on a very, I think you all know, I mean, you did lab too, on a very conceptual level, of course, a pendulum goes back and forth, just the way a mass on a spring goes back and forth and back and forth. We're saying now it really goes back and forth exactly that way, that all the properties are exactly the same. It's just that now the variable, instead of being x positioned on an x-axis, now the variable is theta, angular position, like on the arc of a curve, right? So you have to think differently. But so we start off right away by saying, hey, okay, so this is just like problem one of the exam, what the other person was asking about, right? It's literally the same math. And see there again to Muhammad, there we got that negative sign again. Part of the, I mean, you know something in this class. You know you're making some progress. If you see the idea that that equation staring you in the face right now on the screen is, from a formal structural perspective, the same equation as this, right? I mean, if you've gotten to the point where it doesn't bother you whether it's theta or c, and it doesn't bother you whether it's a number right after the negative sign, or omega squared, or k over m, or in this case, well, this is a number two, or it could have been like G over L or something. If you are getting comfortable that it's, second derivative of a variable, second time derivative of a variable equals negative times constant times that variable, okay, then you already know something in this class. So we're starting with that here. We're saying, okay, pendulum apparently can be described by this differential equation. That seems to mean that it is a harmonic oscillator. Okay. So, and then it gives you like its amplitude, right? It gives you where it starts, but it's telling you in radians, it starts at pi over 10 radians. That's when you start your clock. Now, let me pause on that right there. I don't know how much I say in this in the video, but one thing that makes this problem harder for some people is that now radians are meaning two things in the same problem. It's not a contradiction, but it is confusing. Like, please note, when we say that the amplitude, we're now saying that the dependent variable is theta, by which we literally physically mean place in this circular arc. This radians, this pi over 10 radians that's written in the problem here, that is not anything to do with like radians per second or angular frequency or anything like that, right? And stop me in the chat if that is confusing, or if you didn't realize that, or if you did realize and you don't know like how to deal with that. Like angular frequency is radians because ultimately a radian is ultimately a fraction of a circle, which then allows us to talk about portions of cycles whenever, right? So it is still radians, both contexts, but I don't know how much more to say here. Two things are happening. Something's literally traveling in a circle and it's cycling. So radians are being used both ways in the analysis. It's two different radian measurements. Anyway, stop me in the chat if you want to hear more or less about that. But all right, so then it says draw a free body diagram at an arbitrary point. I mean, I do this in the video, and you do have to review from, we are assuming you still know some fundamentals from physics 1. Like there's two forces, there's always gravity acts on everything in physics, right? So there's always mg pointing down. And then after mg, you draw anything and everything that's touching the mass, the particle of interest, the bob in this case on the pendulum. So the only other object touching the bob, the only object touching the bob is string. And so you draw a string at some angle. Okay, I'm going to pause here too. I don't remember if I do this in the video, but here's a perfect example in terms of your exam. Like question 1 is asking you to draw a free body diagram. It's asking you to draw a very specific type of diagram that we use to solve problems, right, in physics, like a free body diagram. Now, here's the thing. That's a very specific type of diagram being used to solve the problem. I already expect that you're in the habit of doing a 5-step problem solving solution in all these things where you already, the minute you sit down to do a problem, you present a diagram even before you get going with the question or anything like that, even if the question didn't provide one, right? So here's a thing. I'm assuming that you will have already drawn a picture of the pendulum here before you even get to question 1 where it asks you for a free body diagram. Those are two, and that's a first place my eyes are going to go. Does the person have a picture before they even do the free body diagram? Are they similar, the two pictures? Yes, but are they identical? No. Here's the difference. First, you're going to draw a picture of the situation, of the facts, right? Before you're solving anything. And the purpose of that picture is to label every letter that you're going to use in the math throughout, right? Like just like all the other pictures in the other homeworks and stuff. So first, draw like a bob on a string and label the string L and label the bob M and whatnot. And the angle, like the initial angle is pi over 10 radians, whatever. Label everything. And now the reason you just did that for me, now I'm picturing situation. Now I know what you mean by L. Now I know what you mean by theta. And more important, now I know where you're picturing the string to be when it begins its oscillation. Like some of you will draw the string on the right side of a vertical, and some of you will draw it to the left. Totally up to, in other words, some of you are thinking of that way as positive, and some of you are thinking, that is totally up to you. That's totally fine. But I need to know which one you're thinking, because now we go to the free body diagram. Now the free body diagram is just going to have 2 arrows, an mg down and a tension arrow T pointing from the bob along the direction of the string. That T has to be consistent with whichever way you put the string in your first picture. Stop me in the chat if this doesn't make, I mean, it's all like simple once you know, but if you didn't know, then you know that I cared, you wouldn't know. So you draw a picture basically to orient me to your coordinate axes. And so I know, oh, they're okay, at her arbitrary or his arbitrary point that this whole problem is about, the string is like cockeyed that way. Okay, so then they understand that tension's got to pull that way. If you're okay, I'll just keep going. But so there's already a diagram. Then you draw this free body diagram. And yeah, your free body diagram is going to be like mg down, tension up, and to the left or to the right. And that's it. That's all that should be in the free body diagram. That's it. And leave it that way. And you don't have to do components or anything like that. You're going to have to, that gets hard later in the problem, but just do that. Okay. Now, question 2, I'm looking at the time. I think that, wait, I don't think anything else has happened in the chat. So I'm going to keep going with I'm trying to do broad strokes of things that I maybe didn't say in the video, but okay. I'll try to speed it up though. Question 2, it says, what's the angular frequency of this oscillator? That is exactly like that question 2. You're literally doing what you did. So it's back to sort of Muhammad's question and the private chat person's question. Like you're doing the same reasoning that you did in question 1 of problem 1 here. You're really trying to show me that you really get that the minute you stare at this differential equation, the angular frequency omega must be the square root of what's in there, of what's in that constant in the parentheses. So the angular frequency is pi over 6. Right now, this time you don't have to walk through the whole kit and caboodle of the proof. Like now you could say for, full analysis, see problem 1, page 1, whatever. But you're definitely going to get and the angular frequency will be pi over 6. Pro tip, like that's a number. Pi over 6 radians, it means like 3.14 or whatever over 6. It's asking for physics answer. It's not like you're imagining that this is happening in a lab. So even if that constant was expressed into, so make your answer an actual number and round it off to 3 digits, like it says. Like don't leave your answer in terms of pi, whatever, because it's physics. Okay. So that's that one. Then 2, how many seconds should we expect? Same thing as homework 1. If you now understand how to get from omega to capital T, then do that. Now, this is a perfect example too, where of course I'm going to change something in the actual exam. Like here, you notice it's asking how much time to take to get from one turning point to the other. So you have to read the English carefully and realize, okay, he's not asking for a full period. He's not asking for there and back. He's just asking for there So he's asking for a half of a period. So you solve for the period and you take half of that and you explain. And probably that's an easy place for me on your actual exam. I'll change that to say something like from the mass to the equilibrium position or something, which is a quarter period or what, you know, whatever. But okay, so that's that one. Now, okay. I believe, okay, and this is now that, okay, 15 minutes. Okay, we can do this. Yeah, I mean, this is the hardest part of this problem. And yes, I think I do a better job of talking about this in the video Maria posted. I want to use your time. I want to like think of what to say here that wouldn't just be redundant from the video. Okay, first of all, big picture, like the rest of this problem, 5 and 6, are hard in a way, because now we're asking you to step back. Now we're asking you to use classical mechanics, like physics 203 reasoning knowledge, to actually, in a way, show why we're willing to believe this differential equation in the first place. In other words, like, yeah, we're now like we gave the differential equation from part 1, part 2, part 3, and part 4. They all assume that we already believe that a bob on a string acts like a mass on a spring. Now in 5, and we're assuming that we already understand the math of all that we already proved how the math of oscillation works. We proved it already in problem 1. But now it's asking you, hang on, how do you actually know that the math of oscillation does apply to a pendulum? Like, how do we actually know that a pendulum can be described by the differential equation for harmonic oscillation? So I'm going to try to quit. I know I do this. So now we've got to prove something that we haven't proved anywhere else in the exam, because nothing else in the exam was about a pendulum. I'm going to switch the screen now. Hang on one second. I do this every time. Yeah, and so I'm not going to do the whole thing, but I'll give you the thumbnail sketch. But also, and one of these, I know this problem took me many drafts. This problem don't work out perfectly, but finally it got right either last summer or last. I think Maria's right that the video post from the summer is the best version of the video, but also I think you'll find by the time you do your version of this problem, it may even say at the top, it might even say at the top, somewhere not near Earth's surface. Like make a note of this. The broad stroke thing that I'm trying to say is we're about to prove that a differential equation can be used to describe a pendulum. And when we do this proof, then it turns out that the constant in that differential equation is G over L. Yeah, G over L. That's the constant in it. So it turns out, as you found in lab, or as you, I think, now know from lab, it turns out that the angular frequency of a pendulum is like square root of G over L, just like the angular frequency of a mass on a spring is square root of K over M. But first of all, that is not assumed at the beginning of this problem. More to the point, on your problem, it might even say, I'm warning you, it might even say, we're not at the surface of the Earth. So even if somewhere in your mind, like omega equals the square root of G over L, you can't assume that you know what the value of G is. Like, I'm saying this to warn you, part of what's confusing about this problem, or interesting, or pro-tippy about this problem is we're trying to show at the end of the problem. Okay, I'm going to write this down. By part What part is it? By part 5. Yeah. Okay. First thing I'm trying to say is by the time you get to 5, you're trying to show what I just wrote here. You're trying to show that theta can be described by a differential equation of the simple harmonic oscillation form. And when you show that, you're going to end up seeing that omega squared is equal to the square. I mean, that omega is equal to the square root of g over L, just like when you do d2x over dt squared equals negative omega squared x, you find that omega is the square root of k over m. So the first thing I'm saying, if I get hit by a truck right now, is you are showing this. I'll give you the broad strokes of how, but you're trying to show this in part 5, which means in part 5, it comes out that omega equals g over L. The big thing I'm saying is you don't know that at the beginning of the problem. So don't, from any of the earlier parts, start using that pi squared over 36 thing to like figure anything out about G or anything like that. Like that would be a mistake. People do that and it's the wrong thing to do. Well, I'm going to keep going, but let me just look in the chat for a second. Hold on. I see something. Right. Like somewhere under, yeah, I don't remember. It says that somewhere, like in one of the videos. Yes, probably by the time for some reason, this problem was like hard to write exactly right over, but yes, ultimately, probably you're going to be told that you're somewhere underground, where G doesn't equal 9.8, and it doesn't change any of the physics of anything you do, but it means it's stopping you from just like plugging in 9.8 somewhere and thinking you're getting an answer that way. Okay, so that's number one. Now, what are you trying to do in 5? And again, I am watching that. So if this is all we end up doing today, I mean, hopefully this is productive for people. In 5, the basic skeleton of what you're trying to do is, if this was your free body diagram, if this was the pure free body diagram from above, then you need to break something up into components to do F net equals MA on each axis, just like we learned in physics 203. Now, what's hard, I'm going to just say the answer. What's hard is this thing is moving in a curve. This was like what we kind of rushed at the end of class in physics 203, if you had me as a teacher. Well, let me back up for a second. What we definitely learned, what we always do, big emphasis is, whenever you're breaking vectors into components, force vectors into components, the choice of axes is up to us. The axes are up to us. So we always want to choose axes that are, this is Galileo. So we want to choose axes that are convenient for us. When it comes to forces, the axes that are the most convenient are setting up a positive x-axis so that it lines up with the line of expected acceleration. That was a key thing from physics 203, that you always, like on an inclined plane, you tilt your axes so that the x-axis goes along the plane. So when you say F equals ma, you mean A in the direction that's actually happening, like along that x-axis, and you don't have to take sines and cosines of A and stuff like that, right? Well, same thing always in physics. So if something is in a curve, the tricky thing about it being in a curve, if it's curving, that means it's accelerating in a direction that's different from its velocity. To be in a curve means that the way you're going and the way you're going to go are in conflict. That is the essence of a curve. Like if you've ever driven a car, when you're going straight, the headlights are lined up with the tires. Like they're right. You go straight if you're where you're going right now is the same thing as where you're heading or point. But then when you're turning, the body of the car is like that, and the wheels are like that, right? Because the car right now is velocitizing that way, but you're trying to force it that way, right? So to curve is to have a conflict between acceleration and velocity. In other words, to be in a curve necessarily means that you have an acceleration always pointing into the center of that curve, the center of the circle from which that curve is, a piece. So whenever we have curves, we put our x-axis along the radius of the curve. And that is a lot, what I just said. Like, in principle, it's old physics. It's not like the thrust of this class. And actually, yeah, that's good. Direct chat person, like a curveball. Yes, like a curveball is funky because it's like going differently from, yes, it is like a curveball. And this is a curveball. So, yes. So bottom line, when we decide to break up one of these forces into components, the components we should picture are an x-axis along the radius of the curve, and then all other axes perpendicular to that. So gravity, it's like this is like, bottom line, if you're in a little curve, if you think about it, I mean, if you're like a pendulum swinging you're just in a different inclined plane at every moment. You're always sliding at an angle, just a different angle every moment, but you're sliding along an angle. So you should break up gravity the same way we did for inclined planes. That's really what I'm trying to say. So the component diagram that you need to do this will look like this. And you need this now. You need this to do, okay? And so then you do F net equals MA on each axis. On each axis, F net equals MA. Okay, I walked through this in detail on the video, but one of the axes doesn't end up mattering. It's true, like the T mg cosine axis, it's all true things. Like you have T minus mg cosine theta equals MA along that axis. It's all true, and A does not equal 0 along that axis. And if you say it does, or you say those are balanced, you're making a physics mistake. Those aren't balanced, T and mg cosine theta, but they're not relevant to what we're trying to look at here. We're looking at the force that's along the axis of motion, the mg sine. So if back to our diagram up there, this was the angle, right? So to the right is positive, then to the left is negative. But I'm saying this quickly now because I see we have 3 minutes. But what you're going to try to get and explain this from your component free body diagram to F net equals MA along each axis. Along each axis, one of the axes is, well, all right, I'll do, because you don't want to mix this up. This is one axis, but you don't care about that. It's true and it's not 0, but you just don't care about it. You can split, you watch the video but the other one that you do care about is you get this. Okay, and then you walk through a bunch of algebra and approximations that I do on the video where you, where you eventually get and I'm skipping steps. It's all in the video, but eventually you get this. And that statement that you get, we have 2 more minutes. And again, watch the video, but when you get that, that shows, aha, it's an oscillator, and the constant for the oscillator for the differential equation is G over L. I guess we're using a capital. And so that constant must be omega squared. So you've proven it, like you explain all that in English. But by the time you get to that from classical mechanics, then you're saying that's where the beginning of this whole question was justified in thinking of an oscillator, of a pendulum as an oscillator. And then there's one more question, which is not easy, and I'm rushing now because it's on the video, but the last question then says 2 different ways. You have to show 2 different methods for showing how you could actually get the value of G from this whole apparatus. Okay, the 2 different methods. I'll just write them in English now. Maybe I'll have time to do this more expansive on Wednesday or show the video, but it wants you to show that you get the same answer for 2 methods. Same answer. And the 2 methods are energy conservation. And that's where, if you really want to go to town and do the thing of showing that you understand potential energy and kinetic energy, go for it. But one method is energy conservation, and the other method is taking derivative, like energy conservation to solve for V, like we did in homework 1, question 4. And the other is take the derivative, the first derivative of position with respect to time to get V. But notice that, and I'm done, I promise I'm done, but notice that R equals. Okay, that's a fast sketch, but question 5, you have to solve V for 2 different methods, and they have to get to the same answer. Okay, but those were great questions. So hopefully I actually did answer all of them for today. We'll see what we do Wednesday, but thank you all very much. I'll hang out for a second if there's more questions, but hopefully this was helpful. But thank you guys for like studying and stuff. Okay, thank you. Okay, bye. Okay, thank you. Yes, have a nice day. Bye. Okay. Oh, bye. Bye. Okay, I couldn't see. I couldn't see it first. Okay. Bye. Okay, I'm turning off the record.